In this next part of lesson 5-1, we're going to look at how we can include categorical variables in multiple regression models and how we choose the best possible multiple regression model in order to make a prediction for a dependent variable. First, in order to include any kind of categorical independent variable that can be used in the regression model, you'll need to code any categories as numbers. We can't use text in a regression model like we have here for the neighborhood, but we can include text that is coded as a number. For example, if you have a simple yes/no variable, we can create what's called a dummy variable, which is when categorical variables are coded using numbers instead. So if you have only two simple categories like yes and no, we'll just use a number to represent them instead. Like yes is 1, no is 0. I put this other little picture of a light switch in here because creating a dummy variable is like switching a light on and off. The light's off if you're a no, that's what the 0 means, and the light's on if you're a yes, that's what the 1 means. This can create a difference in the regression model so that you use different numbers when that category is met. It's like switching on the light to say, okay, use this number or make this adjustment to the model when this category is true. How you can create a dummy variable from text, like if you have a yes and a no and you want to change it to 1 and 0 instead, is you can use a simple if statement in Excel in order to create that dummy variable. We're going to look at an example of adding a dummy variable to our same multiple regression model to predict sale price. What we want to do is we want to add a dummy variable like yes or no for if the house is in Old Town or not, which is one of the neighborhoods. You can see a house here that's in Old Town. What we would want is a variable that says 1 if it is in Old Town and 0 if it is not. I'm going to insert a new column for that, calling it Old Town ? Meaning is it an old town or not? And I'm going to put it to the left of the sale price. The reason for that is when you perform multiple regression, remember all the independent variables have to be touching each other with no skips. So if I put it over here on the right, then I'd have to like skip over the sale price and neighborhood, and that won't work. So I have to insert it next to the other independent variables. To get Excel to tell me 0 for not Old Town and 1 for if it is Old Town, I use an if statement. If this text here equals Old Town, you have to type it in the same way as the text is here with a capital and the T. Then I want it to be a 1. Otherwise, I want it to be a 0. So if it's an Old Town, it's 1. Otherwise, it's 0. The light switch is off. I press enter, and because we're working in a table structure, you can see that when I do have an Old Town, the variable for the dummy variable is a 1. Most are zeros, but every time we see Old Town, we do have a 1 included for our dummy variable. And that's exactly what we want from the dummy variable, just 1s and 0s representing if that category is true or not. Once you have the 1s and the 0s for the dummy variable, then you can include it in the multiple regression. The multiple regression will save your input that we had last time from the previous sheet, the data sheet, but now I copied and pasted the data into our current sheet just so that I could add in the dummy variable easily. So I'll need to reselect the variable ranges. The Y range is the sale price that we're trying to predict. The X range is the variables from the living area up to Old Town. So before we had 7 variables. Now we should have 8. 1, 2, 3, 4, 5, 6, 7, 8 independent variables to use for prediction. Because I have the data and where I want the output in the same sheet, I can say that I just want the output range to be in this sheet instead of inserting into a new worksheet. It does erase my formatting slightly, but I'll just fix that up. There we go. So this is basically the same output as we had before, except I've now added this extra variable that wasn't there before, my dummy variable for Old Town. What this basically means is we have this extra slope for Old Town. That basically means if you are in Old Town, it decreases the price by $11,435. Better not copy paste that because otherwise it might erase some of the data. But I can summarize it. If house is in Old Town, basically that means if it's a 1, because we're usually talking about a 1 unit increase in the variable. But for a dummy variable, it's either just yes or no. So if the house is in Old Town, then price decreases because it is a negative number by about $11,000 with other variables constant. We can only still change one at a time. Another thing I want you to notice is that by adding in that single extra variable for Old Town, it does slightly change the values of the other slopes and the intercept. So before the intercept was 683,000, now it's 568,000. The slope for living area was 4805, now it's 4794. Another example is lot area is now 0.62, before it was 0.64. Enclosed porch was negative 11.98, now it's negative 9.4. So they're all around the same magnitude, no like gigantic changes, but I just want you to know every time you add or if you take away a variable, it does change the values for your coefficients, either the slope and the intercept, slightly every single time. So that leads us to the next question. Now we have this model that includes the 8 numeric variables, or 7, sorry, and this new model that includes the 7 numeric variables plus the 1 dummy variable for Old Town. So how do we know which of these is better and which model should we use for prediction? So there is actually a method for finding the best multiple regression model. And that involves using this output that may or may not look familiar. So this output in both of this ANOVA and here where you see t-stat and p-value are hypothesis tests that are conducted about the regression. So before study week, we talked a lot about inferential statistics and hypothesis testing, including t-tests and ANOVA, and those concepts are used here to test if the regression model is good or not. The statistical word we use for good is if it's significant or not. So because this is related to inference and hypothesis testing, the first step to find the best regression model is to pick a level of significance. We call that alpha, and we usually almost always use 5%. Then you run the regression with all possible independent variables included. So because we added this one for Old Town to get 8, the most I can include is 8. So first you start with all 8. This output was be what we start with, all 8. Then we're going to look at the hypothesis tests for each of these coefficients, each of these slopes. What the hypothesis test is doing here with the t-stat and the p-value is it's testing if this slope is significantly different than 0 or not. The null is that the coefficient would be 0. The alternative is that it's not 0. If the slope is essentially close enough to 0 that it is not significant, then it means we shouldn't really include it in the model. So essentially what our decision should be from this p-value is if the p-value is less than alpha, then that means this slope is significant, included in the model. But if this p-value is actually greater than alpha, then that means that we do not reject the null and the coefficient is approximately 0, which would mean that it doesn't do anything to the model. If you add in a 0, it makes no difference to the predicted price, so in that case we can remove it. If you find a variable to remove, you'll remove it and rerun the regression. What you have to be careful about is you can only remove one at a time, because every single time you add or remove a variable, all the numbers change. So you can only remove one at a time. How it works is you remove the one with the highest p-value bigger than 5% first, and you'll go one at a time until all the p-values are less than 5%, the level of significance. Once you have cut all the variables that have p-values that are not significant, that are greater than alpha, then we'll look at some other information. To get the best model possible, all of these p-values need to be less than 5%, but also in this ANOVA, it's testing the full regression model, not just the individual slopes, but the full multiple regression equation. This significance should also be less than 5%. And finally, something else we check is the association in the model. The R value is normally our correlation coefficient, but because we're using multiple independent variables here, instead of looking at just the regular correlation coefficient, we look here at the adjusted R squared. The reason we look at the one called adjusted is because the correlation coefficient actually will always go up if you add more variables. So when you switch from having, like here we had 7 to having 8, it will always go up even if it's just slightly. So the reason why we have what's called adjusted R squared is it does not artificially go up just because you added another variable. This one captures like a more standardized, or what they call adjusted formula, so that even though you added variables, it won't just keep going up every single time you add them in. So this is what you can look at to see if you have like a strong correlation or not. And that's how you decide on which model is best. So first you'd start with the full regression model. So I'm just going to copy the same output from earlier and paste it, but I'll get rid of the color so you can kind of start from the beginning. So the first step, once you have your full regression model with all possible x's, we have 8 of them, is step 1 is you'll look at the p-values for anything bigger than 5%. This one's in scientific notation, 1.7 times 10 to the negative 8, so it's very small, almost 0. It's less than 5%, so the intercept's good in the model. For the living area, it's 7.85 times 10 to the negative 70. That's essentially 0. That means this variable is significant. It should stay in the model. The slope is significant. It is not 0. Stays in the model. All of these are in scientific notation to be very small numbers, close to 0. That they are all less than 5%, so they should all be included in the model. But the next one, enclosed porch, has this p-value that is actually a lot bigger than 5%. It's almost 60%. So the p-value here is bigger than 5%, which means we can remove this one. The next one for Old Town is also less than 5%, so it's good. So really what we want to do is just remove enclosed porch and then rerun the regression model. If I wanted to rerun the regression model right now, I'd want to include these 6 variables and then Old Town. But remember, when you use the data analysis tool pack, you're not allowed to skip. So if I'm removing enclosed porch, the easiest way to not use it is just to delete that whole column. And then the 7 variables I do want to include are now all in a row without skipping, which is how they need to be formatted for the data analysis tool pack. So for my input Y range, I just need to change it to column X instead of column Y because I deleted a column. And for the X range, instead of Q to X, now it needs to be Q to W. Again, because I deleted a column. For the output range, I'm going to place it here where I say model number 2. So with model number 2, the first thing you're going to look at is all the p-values. All the first ones, 1, 2, 3, 4, 5, 6, 7, are all in scientific notation. Very, very small numbers, less than 0.05. Old Town, 0.007, also less than 0.05. So all of these values are what we call significant. All that means is they have p-values less than 5%, so we include them in the model. There's no more to delete. Once you've established that there's no more to delete, you should also look at the p-value for the overall regression. That p-value is also less than 5%, which means overall regression is significant. It just means it actually makes sense to predict price based on these multiple x variables, based on the 7 we have. Finally, look at the adjusted r squared. Like I said, we look at the adjusted because otherwise, usually when you include more variables, it always increases the r squared. This one has an r squared of 0.77385. Before we were at 77374. So it slightly went up, but this means it's a positive strong correlation because we have a positive number and it is close to 1. So this would be our best regression model for those 3 reasons. All the p-values for the individual x variables are significant, which means they should all have slopes included in the model. The ANOVA is for the overall regression. Can you predict price based on these other things? This one says yes, it's significant because the p-value is less than 0.05, and the adjusted r squared shows we have a strong positive correlation. Now that we've found our best model, we can use it to make a prediction. To make a prediction for the dependent variable, you're just implementing this equation. That means you start with the intercept, and then you add in every single slope times a given value for that x. Keep adding them in for however many slopes you have. You do have to be careful with selecting the cells in Excel so you don't make a mistake. So if I want to predict the sale price based on these facts that I made up about a house, that it has a living area of 2,500 square feet, a quality of 7, it was built in 1999, it can fit 2 cars in the garage, it has basement square footage of 2,500 square feet, lot area of 8,500, and it is located in Old Town. How we would type this in is you'd start with the intercept, and then you take each slope, so the slope for living area times value for living area. Then you add in the next slope, overall quality, times overall quality. Then add in the next slope, year built, times year built. Slope for garage cars, times number of cars in the garage, plus slope for basement square footage, times the basement square footage selected, plus slope for lot area, times the 8,500 lot area, plus if it's in the slope for Old Town, times 1, meaning that it is in Old Town. If I press enter, this gives me a predicted price for a house with these exact features, which should be $283,731.15. What's nice about using the formula approach is you could change this for another house. If you wanted a big house that was 4,000 square feet, that had a really high overall quality of 9, that was built in the year 2008, it can fit 3 cars in the garage. Again, it has the same square footage for the basement level. It has a small lot because the house is so big. So let's say only 1,000 lot area, and it's not in Old Town. The predicted price is now $461,450.78, but I didn't have to update the formula. It still works. Or if I go back and change all the numbers back to what they used to be, the ones I had originally given you, I get back to that original formula for the sale price. So that's how you always have to make predictions for multiple regression, is you take your intercept and then every single slope individually times the value and keep adding in slope times value for however many slopes you have. To help you better understand the process of finding the best regression model, I have a learning check question for you. In this learning check question, you'll be dealing with 2010 Major League Baseball statistics. You want to find a model to predict how many times the team will win. So you're predicting this variable. This is your y. 1 is y. And you're going to first start by including all possible numeric variables as x's. So these here. You'll have to eliminate variables until they're all significant, following the process for choosing the best possible model. Here where it says predict, these are the values like I gave you in the table here that I want you to make a prediction, but only once you have found the best possible model. So please pause the video here, and then when you press play again, I'll show you the answer. Okay. So if I wanted to solve this problem, I would start with the full regression. The Y range I'm trying to predict is if they won. The X range is every other single numerical variable. Don't select the predictions because, like I said, we only use that at the end to make a prediction once we have the best model. For the output range, I'm going to put that right beside this table. So I start by looking at my p-values. I want anything that's not significant. So this one's bigger than 5%. This one's bigger than 5% at 6%. This one's 9.7, so it's bigger. This one's bigger than 5%. This one's bigger than 5%. This one's bigger than 5%, and so is this one. So we have a lot that are bigger than 5%, but you always want to start with the worst one. The worst one will be the highest p-value, and that's RBI's, almost at 93 for the p-value. So this one is the worst, so it goes first. So if you want, you can just delete the RBI column, and then we're going to do the regression again with RBI removed. So instead of stopping at K, we now want to stop at J. And for the output range, I'll just put it on top of the old stuff. There we go. So it's replaced. Now again, all the numbers will slightly change once you remove a variable. So I'm still looking for any p-values higher than 5%. So strikeouts is higher than 5%, walks is higher than 5%, triples is higher, doubles is higher, and home runs is higher. Because we still have quite a few in the red that are higher than 5%, I remove the highest one first. Triples is at almost 82%, so it's the worst. So triples goes away. And then I'm going to rerun the regression again. Instead of going to column J, I'll go only to column I. And for my output range, L5 is where I want to put it on top of that one. Now again, all the numbers change. So with that change, we have fewer that are in the red. Walks is higher than 5%, doubles is higher than 5%, and home runs is higher than 5%. Doubles is the highest though. It's at about 63%. So it will be the next one that I delete. Delete. And do the regression again. This time I'm only going to column H, and my output will change to K because I deleted a column again. And I'm still looking at my p-values for every single variable individually. Now I've only got a couple higher than 5%, walks and home runs. The higher one is home runs at 13%. That's higher than 5, so I'll delete home runs and run the regression again. This time I only need to go to column G, and the output will change to J5. Every time you remove or add a variable, it changes the numbers. So before hits was okay, but now it went back over 5%, and walks is also over 5%. Walks is the one that's higher though at about 27%, so walks should be deleted next. By to the walks variable, and I run the regression again. Now I'm down to column F, and my output will be I5. I just replaced the other one. And this one is less than 5, less than 5. Hits is greater than 5, less than 5, less than 5. So the only one I have left that's greater than 5 is hits at about 12%. So I need to delete hits. By to the hits. And now I'm only going to column E. My output range will be H5. And I check my p-values. There we go. They're all less than 5% now, meaning that all of these variables should be included in the model. That it makes sense to use runs, strikeouts, and the earned run averages to predict if the team won or not. If I look at the overall significance of the model, it's extremely small, close to zero. What that means is that it makes sense to predict the wins based on these three variables I have left. Another way of saying that is that the overall regression is significant. And finally, the adjusted R squared is also a very strong positive correlation. There we go. If you also wanted to do interpretations of the slope value, just make sure this is all in black so you can see it. If you want to do interpretations, you have to remember how we interpret these values. For the intercept, it's always your value for y when all the x's are 0. So here we're trying to predict wins for y. So this would be that you have the 80 wins when runs, strikeouts, and the earned run average are all 0. So if those three x variables are all 0, then what we're predicting the wins will be this number. For the first slope, this means when runs increase by 1, we're always increasing by 1. We have a positive slope, so that means wins increase by about 0.1. So if you increase by 1 run, like you get one more run, then you have about a 0.1 chance higher of winning. Like 10% more chance of winning for each run. For the strikeouts, when strikeouts increase by 1, your wins actually decrease because it's a negative slope, but only by 0.01. It's a very small number. Probably because this means when your team strikes out, then your chance to win goes down, which makes sense. The more you're striking out, your chance to win is going down. And then when the earned run average increases by 1, again, we have a negative slope, so that means your wins decrease by 14.27 with all other variables constant. And that's what these mean. The intercept is always your value of y when the x's are 0 and we only have 3 x's left. And each of the slopes are when you change this variable that's listed here by 1, how much does the y change? So the y is if you won the game, how many wins you have or not. Finally, the very last thing we've learned is how to make a prediction. We can put that prediction here. In 2019, Arizona had 269 runs, 84 strikeouts, and an earned run average of 3.52. We want to predict how many times they won. How we do that is using the equation of the line, which is intercept plus slope for runs times number of runs given, plus strikeouts times number of strikeouts given, plus earned run average, slope times the earned run average value given. I know it's very hard to read in the red box, so I would recommend looking up in the formula bar. And that gives you the full formula where you have intercept plus slope times value, plus slope times value, plus slope times value. We do it 3 times because we're left with 3 x variables. And this predicts that Arizona in 2019 won about 56 games. If we look online, in 2019, Arizona actually won 85 games, not only 56. but we were using data from 2010 for this prediction, and then this was in the 2019 season. So that's actually quite considerably later. So perhaps we're predicting too far outside of the range, too much extrapolation to clearly see or be able to clearly predict that much in the future how many games they would win in 2019. But using the results of the multiple regression, we get this prediction using the equation for 56 wins. So that is the process for multiple regression that you'll always engage in. Sometimes you can add in categorical variables using the dummy variable process. Then you need to decide on the best regression model, where you have to go through an iterative process by deleting one variable at a time until they're all significant. The overall regression model is significant by looking at the overall p-value in the ANOVA table, and you want a high adjusted R-squared. Once you have found your best model, you can use the equation of the multiple regression line to make a prediction. We'll continue to use multiple regression when we learn about time series analysis in the next lesson. Thank you for watching this video, and this concludes lesson 5-1.